All right, counting. So let's start here.
Chapter 3.
No, we are still chapter 2. We're finishing chapter 2. Counting. Counting. When we are talking about counting, we have to start talking about possibilities. And a very simple example is a coin toss and a dice roll. Right? We have a coin toss and a dice roll. Both of them easy. How many choices we have of our outcomes of the coin toss? 2, dice roll, 6. What's the sample space for if I do them together? Okay. Well, I hear 12, but I hear some non-convinced 12 and some serious 12. So if we are talking about sample space, what's the definition of sample space?
Or the possibility. Number of outcomes.
All the possible outcomes. Right, so this is all outcomes. So if I ask you what the sample space for this is, I'm asking you what all the possible outcomes are. If we don't know any better, well, we're going to flip the coin first, heads or tails, and then we're going to roll the die. And we get 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right? So we have head 1, head 2, head 3, head 4, head 5, head 6, tail 1, tail 2, tail 3, tail 4, tail 5, tail 6. So we're going to get eventually 12 outcomes. Okay, but drawing a tree diagram every time is just, it's a waste of time. So we're going to start looking at it from a theory point of view, and we're going to look at the fundamental counting rule. And fundamental counting rule says if you have an event that can occur m ways and another event that can occur n ways, together they can occur m times n ways. In our case, head can outcome, there's 2 outcomes for head and tail, and there's 6 outcomes for a dice, together m times n, 12. Let's do an easy example. iPhone locks. The first time the iPhone got locked, you could put 4-digit PIN. The first one couldn't be a 0. So 4-digit PIN, first digit can't be 0. How many combinations were there possible?
Only one digit. Can't be 0. That's 90.
90.
9 characters.
Yes.
Using 4 pins.
Yeah.
9,999.
No. How many choices do we have for the first digit? 9. Right? We have 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8. So it's 9. Second one, it can be 10 because we can have a 0. 10 and 10. And fundamental counting rule says, hey, m times n. So m times n, right? And we keep on multiplying it out. So what we are getting is You have 9,000 combinations. You have 4 digits, and the first one is not 0. Okay. What's the probability I will be able to break into your phone on the first try? Don't shake your head. I need a number. This is a...
9,000.
Sorry?
1 in 9,000.
Yes. The probability of getting it right is, right, only one combination unlocks your phone, and there's, so 1 out of the sample space, which is 9,000. So 1 out of 9,000. That's not bad. What, about a year ago, iPhone changed it to 6. Android has been running on 9 for the most part, right? If you apply to CIA, you need a 47-character password. Right, so we have ways to go. All right, let's try one more then. Let's put it over here. Let's say we have 5 digits. First digit can't be 1 or 0. And then last digit cannot be 0. So if you have 5 digits, first digits cannot be 1 or 0, and the last digits cannot be 0. How many combinations?
8.
So again, we go 1, 2, 3, 4, 5. First one is 8 because we're losing 2. 10, 10, 10. The last one cannot be 0, so we are left with 9. We do the multiplication and we come out with 72,000. Four-pin iPhone gives you 10,000 combinations. 6-pin iPhone gives you 1 million. Chances go up. If you're looking how to cover, 1, 2, 3, 4. Okay. That's not bad. Let's look at this. How many of you played Scrabble before? How many of you know of Scrabble? Okay. How many of you cheated on Scrabble, made words that are almost exactly what they should be, but maybe a letter off? I'm dyslexic, English is my third language, so I make up words all the time. But let's say you're really, really desperate, right? You started betting your house and your car on the line, right? You're getting really desperate in Scrabble. Serious games, Scrabble, serious games. And what you're left with is an A, a B, a C, a D, and an E. And you're really, really desperate, right? So my question is, how many combinations of those letters can I make? And I don't care if it's a word or not. I just want to put 5 letters on the board in a row. And I want to score all the triple points, double words, points, everything. I want to just mac it. How many combinations can I have of those 5 letters?
Wait, I thought in practice or
5
theory?
times 50. No, more than that. 5 times 5 times 5 times. Is it 5 times?
No, only 1 times 5 times 4 times 3.
Yes, because if we have 5 words, right? We have a word that has 5 letters. How many choices do we have for the first letter? Well, we have the whole bar, so we have 5. But once we use that letter, we cannot use it again. 4, 3, 2, and we don't really have a choice for the last letter. It's 1 because there's only 1 letter left. And so what we are coming out is that we can form 120, right? 5 letter, and I'm going to put words in air quotes. Right? Again, you're desperate. Anything goes. Just I want to put it down. We all been there when we played Scrabble. We just kind of make things up, hoping it will pass. Yeah, my brother introduced me to this online game where there's an actual automatic dictionary, so it just kind of spits it out. Apparently, my version was bugged because after 10 tries, it tells you something nice like, where did you learn English, or do you speak any? So it has one of those reminders. But anyways, so we have 120. Now, 120 letter words, right? Which is what? Which is 120 different arrangements of unique items. And arrangements and unique are important words in this case. Okay. Now, 5-letter words and writing 5 times 4 times 3 times 2 times 1, that's okay, right? It's relatively easy. What happens if you're starting to work for CIA and you decide to crack crypto codes, and you know for a fact that the password for the banking is 20 characters long? And you know those 20 characters, you just have to arrange it. Writing down 20 times 19 times 18 times 17 times 16 times 2 times 1, it's going to take a lot of space. We're lazy. Good scientists are lazy. And what we are doing is we say, hey, we can shorten it. So a 5 times 4 times 3 times 2 times 1, we can write it like this. And that exclamation point is called the factorial. So 5 exclamation point is read 5 factorial, and it means 5 times 4 times 3 times 2 times 1. Now, if you have a calculator with you, I'll gladly point out where you can find it, but you should know where it is on your calculator. If you have a TI 30 version, that's under PRB, which is upper left corner. If you have a TI 84 or 83, it's probably going to be under math, and then you have to scroll over to probability. Let's see. Found it?
It's a PRB, right?
Yeah. And then you just scroll to the exclamation point. So you have put a number in the exclamation. You found it?
Yeah, I found it.
Cool. You found it? Good. You?
Nope. Wait. It's stuck. He's on. Come
Okay.
on.
You got it? Yep. I'm coming.
That'll be divided.
Yep. So
So how
you
would I
go
do it?
5, shift this, and it just gives you the answer.
Oh, okay.
Hold on.
The exclamation point.
Oh, that.
Uh,
I don't think this one has it. Nope.
It's not on.
Yep. Trying to find the button for this one. Damn, there's a lot. Get a different calculator.
No, I'm sure it is here somewhere. Okay, shoot me this in an email. I'll find it for you.
Okay.
Oh,
What calculator is it?
right here.
There we go.
So okay, you don't have one.
6.
No, under 3. So you go 5, second, this, and it gives you the answer.
Okay. So it's above the 3.
Yeah. Okay. You're sorry.
Is it on the iPhone?
Since you're not going to use iPhones for quizzes and exams or the final, that's a question I don't want to answer unless you were using it for homework. But if you're using an iPhone for homework, you're probably playing games too. So, anyways, so this is it. Okay. Now that requires, unfortunately, one little definition. Just so we are above par. And the definition says, hey, if we have 0 factorial, how many arrangements of 0 unique items can I make?
One.
1. So 0 factorial is 1. So that's an important little bits and pieces. Okay. So
Put the factorial into the calculator when you solve a problem.
so you plug in the number, then you punch in the factorial. And then on some calculators like yours, you probably have it typed out. In the ones, the different ones or ones you will right away get the number, the actual number. So right, Sunny, you get a number. You get 120. You don't get 5 exclamation point and then you press enter. In your case, you will get the exclamation point. So that's that. Again, if your calculator breaks, I have one that I'm willing to borrow out if people need it. All right. So for any set of n different unique items, there are n factorial So for any set of n unique items or different items, we have n factorial different arrangements possible. Okay, one more example of this, or good?
One more.
One more? Okay. On your trip to mainland, you want to visit 7 states. How many ways can you visit all 7? Again, 7 spaces. Go. Okay, so let's look at next piece. Permutation. When we talk about permutation, we're talking about a different arrangement of items. And we already talked about it, so n unique items gives you n factorial arrangements. Which are also unique. So, example. How many of you have extended family? Bigger than one, right? If you have extended family, you have uncles, aunts, nieces, nephews, grandpa, grandfather, boyfriends, third ex of, from the second marriage, kind of big network, right? What happens if you want to visit only a part of that family? So let's say, as example, out of 58 people in your extended So out of your extended family of 58 people, you only can visit 4. How many ways can you do so? Now, if your family is any way like my family, Aunt Julie will get pissed if she's visited as a second person versus a first person, right? My grandma is like this. If you don't call her 4 seconds after midnight, she assumes you called somebody else before her. She doesn't send you Christmas presents. Like she forgets to send you, a card for your birthday. So arrangement is obviously a matter. So how do we do it? Well, we're going to do it the same way we did the previous problems. We have only space for 4, so that's the 4. How many choices of family members do we have for the first one? We have 58. Right? We have big interest. How about the second one? Well, one down, 57, 56, and 55. So how many ways can we do it? Well, it's 58 times 57 times 56 and 55. For people that are curious, there's 10,182,480 ways you can visit 4 members of your family, of your extended family. If your extended family is 58 people, okay. Suddenly sending, thank you cards and happy Christmas cards, becomes problematic. It's a long way to go. I'm going to put a little
Is there a button in your calculator that you can press to do it like that? Because you're just limiting it to 4.
Yes, but we're getting there yet. Yes. We're not going to be doing this every time by hand because it's just a waste of your time. It's supposed to be decision making and not accounting. All right, so let's talk about this. So if we look in permutations, well, we need a couple of things. First of all, we need n different items. So the first thing is we need. Then we need a symbol to represent how many ever we're going to pick. In our case, it was 4. So we need an R. So we have an N, and we have an R. And then R is the number of items to be arranged. Out of N. And third thing is we need to remember that the arrangement matters. So arrangement order matters. Now, I can give you the formula how to do it, or we can come up with the formula. How do we come up with the formula? If we had 58 to be arranged in 58 spaces, what do we have? 58 in 58 spaces is 58 factorial. Yes? N items in n places, it's 58 factorial. Well, yeah, we're getting there. Now, if you look at 58 factorial is what? 58 times 57 times 56 times 55 times 54 times 1. Right? It's this 58 factorial is this really long chain. In our case, we only focus on the front of it. So we eliminated this 54 factorial. Right? 54 times 53 times 52. So we eliminated this. So we divided by 54 times 53 times 52 times 1. 54 times 53 times 52 times 51, it's 54 factorial. Right? How do we get 54 factorial? Right? That's this. How do we get this? Well, let's look at the letters. If you look at for the letters, it's n choices. What's 58 minus 4? 54. So what you get on the bottom is that. And that's the formula. Now the reason why I'm telling you how to get to this formula is just in case you get stuck. So you understand where you're getting the mathematics from. And the symbol for that is NPR. Now on the TI 84s, 83s and 30s, you punch in the N, then you press the NPR button, then you press the R button. On others, I would have to take a look what you have on your calculator. But there should be a button for it. Most calculators will have the button for it. Now, just in case your calculator doesn't have a button for it, or your calculator dies halfway through homework or halfway through exam, I'm happy if you give me this. If you say, hey, this is 58P4, and then you expand it like this, and you give me those numbers. The actual number calculation is great, but it's not the valuable part. For me, the valuable part for this problem is if somebody says, hey, 58P4, which is 58 factorial divided by 58 minus 4 factorial, which is equals to 58 factorial divided by 50. You get to here, I'm going to give you full credit. I would like the number because it's easier to check a number. But if your calculator dies or you borrowed the wrong calculator that day, if you get to here, I'm going to give you full credit unless I'm asking for a specific number. Because again, for me, it's important that you know how to do it versus actually doing it. Okay. Now, on some older calculators, you might want to be inclined to calculate this by saying 58 factorial divided by 54 factorial. Most older calculators will die when you punch in 58 factorial, because 58 factorial has 78 zeros. It's a big number. So some older calculators will die. If they have a button, they will work. If you just punch in the wrong numbers, might not. So just be aware of the fact that this number gets really, really big. Okay, so we have permutations. Let's do an example. Let's say, as an example, let's say we have 10 students running for student government. And by student government, I mean president, VP, secretary, and treasurer. Right? So question is, how many ways can the government be arranged? So we have 10 students running for student government, which is president, VP, secretary, and treasurer. And question is, how many ways can we have the government arranged? Ten P4, right? 10. We're choosing 4 out of 10, which is 10 factorial divided by 10 minus 4 factorial, and in our case that comes out to be 5040. So there's 5040 distinct ways we can arrange 4 people out of 10 in this case.
Yeah.
Coming back? Okay. Okay, more. Let's do more. Relative, student, government, all great. Let's look at something a bit more abstract. Let's say we have, let's make it bigger. Let's say we have that. How many ways can I arrange this? It's 10 objects. 10 P3 implies 3 objects out of 10. I'm asking you to arrange 10 objects out of 10.
3,628,800, right? So it's 10.
3 million?
Wait, no, I didn't.
No. Okay, so if we approached it the way we've been approaching problems, right? The answer is there's 10 objects, 10 places, 10 factorial. Right? That's what everybody is going to aim towards the first round. Okay, in this case, let me tell you a story about Billy, Bob, and James. We had Billy, Bob, we had Billy, Bob, and James. If we have 3, I name my squares, don't judge me. If we have 3 unique squares, how many ways can I arrange them? How many ways can I arrange those 3 squares? 6. How did you get that? 3 factorial, right? We talked about n unique objects produce n factorial unique arrangements. Everybody's comfortable with. What are those arrangements? I'm going to use dots versus squares so it's faster. Six unique arrangements. 1, 2, 3, 4, 5, and 6. Everybody happy about this so far? So we got 3 factorial. Now, what happens if I just mix Bob and James together? I mix those two together. You sure? How many options do I have now? If instead of this I have that.
You just have one option?
No. What happens if I have this? If I have this, how many options do I have? Well, those two are the same, so that's 1. Those two are the same, that's 2. And those two are the same, that's 3. Yes? So I have 3 options. 3 options. Not 3 factorial, 3 options. Everybody happy with this so far, how I got there? Yes? So how many options did I lose? 3. Or I lost half of them. I went from 6 to 3. Because the moment I turn 2 of those squares to be not unique anymore, I lose those 2 arrangements. So I lose 2 factorial arrangements. Right? Think about it this way. If you have if you have 3 arrangements, right? This is different, right? Those are the 6 arrangements. Right? What happens if I have 3 like this? This is an arrangement, yes? Everybody agrees. Now, is it the same arrangement? Yeah, no, I moved it over. How about now? Right? I have 1 arrangement. So instead of 6, I have 1. So in our case, when we're looking at this, we say, hey, those 3 things, I won't be able to tell them apart. So I'm losing those arrangements. How many arrangements? 3 factorial. Almost. Sorry. No, but there's more. I have the 2 circles. Can I tell the difference between the 2 circles? No. How many arrangements can 2 objects make? 2 factorial, right? So I'm losing 2 factorial afterwards. And the third option, right? We have 5 triangles. How many factorials or how many arrangements can those do? 5 factorial, right? So I have 10 factorial arrangements because I can arrange it, but then I'm going to have to cut down because things start looking the same. Questions? Yes, no, maybe. Is everybody comfortable with this? I see blank stares here and there. I don't know if I'm talking too loud. Okay. There is no button to calculate this, at least not on most calculators. So what we usually do with this, we calculate by hand. So 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. And then 5 factorial is 5 times 4 times 3 times 1. Now, the reason why I write that 1, even though multiplication by 1 gives you the same number, is for me to know that this is a factorial. If I write the 1, I know it's a 3 factorial. And then we just take it apart. 5 times 4 times 3 times 2, and this and this cancels out. 3 times 2 times 1, 6. So 6 gets out here. And then 2 times, and then 8. It's a 4. So we are coming out to be 10 times 9 times 4 times 7. Which comes out to be 2,520.
Did you cross out the 2, 1 again?
2, 1, and 8. Okay, I'll color code it. So this, and I got a 4. And then this and this. But anyway you want to reduce it, you can reduce it. But you can reduce the fraction. And this is much more manageable than this. Now for things like this, I'm very happy if you get to here. I would like to see this, but honestly, this is the important part. Can you realize that things are similar? Okay. Plowing along. So for n, for non-distinct items, distinct items. You get n factorial divided by we have some version of this. And so n is the total number of items, and n1, n2, nk are the counts of, how do they refer to it? Counts of non-distinct items. Okay. So we get this fraction going on. So on top is all the items, on the bottom is groups of what wasn't distinct. All right, so here's the question. What's the most awesome word that has 10 letters? What's the greatest word with 10 letters in it? Okay.
Sorry, what was that word right there before? Oh, the cat?
Statistics?
Which one? This one?
The one before of the count?
Counts?
Counts.
Sorry.
No worries.
Statistics. The most awesome 10-letter word. You're in this class, it must be awesome. Statistics. So my question is, how many ways can we arrange those letters? You have a 10-letter word, we want to scramble it up and arrange it. How many ways can we arrange it?
Oh, there's 3 X's. Count for that. 10.
Or how many different? How many different ways can we arrange these letters? Well, we start from the scratch. Total count of all the letters, 10. 10 factorial. And what are we taking out? Well, there's 3 S's. So 3 factorial for the S's, right? There's 3 T's. So 3 factorial for the T's. And there's 2 I's. 2 factorial for the I's. And for people that want to calculate this, it comes out to be 50,400. Questions? Is everybody okay with this? Now, if you look at that monster pocket of a homework, 2, I think it's at this point, and you look at question 49, 49 has the 2 words. There are 2 words in Polish. It's a first name and a last name. That's a combination that is most difficult to pronounce for foreigners. Question 49 on the homework. It's pronounced Grzegorz Brzęczyszczykiewicz. First and last name. And since you guys misspelled my name already at least once, in at least one email my name got misspelled, I figured, So how many ways can we scramble those letters? And this is the question, this is exactly this question. Right? Now again, do I need you to calculate this for both of those? No. I just need this. So for question 49 and on the questions on the exams and the final, I'm looking for this, I'm not looking for this. This is nice. This is nice. But with 18 letters, I think, for the last name, that's just a huge number and it's a waste of your time to do it. So I'm looking for this. If you can assign which one is for what, that makes it easier to grade, and if you miscount something, it's easier to give partial credit. But I'm looking for this, not this. So again, Grzegorz Brzęczyszczykiewicz comes to the rescue, and you guys get to enjoy it. Polish, the hardest language on the planet. Well, after Chinese, maybe, but it's one of the hardest languages on the planet. Hey, no problems. So we're talking about statistics, and most of us are trying to do something with it. How about start a family? So how many ways could you plan a family with 7 boys and 5 girls? How many ways could you plan a family with 7 boys and 5 girls? I'm waiting. So how do we do it?
12 permutation over 7 permutation times 5.
12 kids? Well, we are planning the boys, so they're really not very much distinct, right? So 7, and the girls aren't distinct either, right? Once they're born, those are human beings, they're individuals. When we are just planning them, so how many ways is that? Now, if you want to do the math for this, that should come out to 790. So if you have 1 planning meeting a day,
Complete that statistics. Do 10 permutation over 3.
what do you mean completed?
Do the long math, because I'm trying to cross out all the.
Okay.
I have 3, 2, 1, 3, 2, 1, and 2.
10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by, there was 3, 3, 2?
3.
Yeah. So 3 times 2 times 1 times 3 times 2 times 1 times 2 times 1. Okay, so 3, 2, 1, 3, 2, 1. 3, 2, 1, 6, and 2, 4, and I get a 2 out here. So I get 10 times 9 times 8 times 7 times 5 times 2.
That's the step I did.
Okay.
But the last time you wrote a 4 instead of a 6.
Last time I was 8 divided by 2, so I got a 4.
Oh, yeah.
It's 4 divided by 2, that's 2. I like numbers, so that is easy for me, but that's not always the case for everybody. Are we comfortable with this? Yes? You sure? Yep.
What do you try to get that number?
How do I get this number? Actually, I'm going to use a little shortcut here. I'm just going to go 7 times 6 times 5 times 4 times 3 times 2 times 1. That's 7 factorial. So I'm just going to shorten it out. And that comes out to be 7 factorial times 5 times 4 times 3 times 2 times 1. So 7 factorial here, 7 factorial here. 5, what do we do? 4 and 3 gives me 12. And 5 and 2 gives me 10. So that's 11 times 9 times 8. Not everybody has to be great with numbers. Careful and you're going to get it. Now, quick announcement is that statistics has, as far as I divided it, statistics has 5 chapters. From my experience, most people are really good at one of those chapters, and they're okay with a second, and the rest of it is, oh my God, what am I doing with my life? There's very rarely people that don't get any of the chapters, and there's very few people that don't get it. So either if you get everything or you don't get everything, you need to talk to me. Most people will be okay with one, like they will like this counting, or they will like the tables for the distributions, or they will like z-scores. But everybody has a little nook and cranny that they're good at, and the rest is somewhat more difficult. So just talk to me. The more you talk to me, the better it is for everybody. All right. This is good. So sometimes order does not matter. Well, since you guys are the gambling class, let's talk about horse races. Okay. So you bet. You bet on 5 races out of 25 horse races available. So you're betting on 5 races out of 25 horse races available. How many combinations of 5 races can you select to bet on? You don't care if you bet on this first or second, you just want to place 5 bets. How many ways can you do that? Right? When I was with my bookies, you tell him exactly which races you want to bet on, and you give the money, right? And it doesn't matter which bet you place first, which bet you place second. You want to pick 5. And so we are getting to this corner called combinations. Well, combinations are having very similar rules to permutations. Well, first one is we need n distinct, unique items. 2, we need to pick a number of those items that we're going to arrange. So is R is the number of of selected. And free arrangement does not matter. And what that means is A, B, C is same as C, A, B. So for combinations, we still have unique items. We still pick a piece or all of it from it, and the arrangement doesn't matter. As you probably predicted, on our calculators, the button would be NCR. And NCR looks very much like NPR. So we have n factorial. Then on the bottom, we're picking only R of them, so n minus R factorial, because we're going to cut off the tail of things we don't need. And last piece is this. Non-distinct items. If we don't care about the arrangement of the bets, in this case, right? We could bet 1, 2, 3, 4, or we could bet 4, 5, 1, 2, 3. Those are the same things. So we're losing the distinctness of those 5 items. So we have one more thing here, which is R factorial. So we're losing the distinctness. Right? This is the permutation, so this is permutation. And this thing here is the loss of distinctness. You lose the distinctness, right? If you don't care that you're picking those 5, in what order that you're picking those 5. So in our case, that will be 25C5, which will be 25 factorial divided by 25 minus 5 factorial, 5 factorial. Which comes out to be now there's a button for it on your calculator. It's probably in the same region as the NPR. Questions?
Is that times 5?
Yeah, this is times 5 factorial. Right, so it's the same as permutation, just in permutation we cared which one came first, which one came second. Now that we don't care, that order doesn't matter. If the order doesn't matter, we lose the distinctness. We look towards the same thing. Yes?
So the long way to solve that is 25, 24, 23, 22, 21, 20 divided by 5.
No, 21. 25 times 24 times 23 times 22 times 21 divided by 5 times 4 times 3 times 2. But you have NCR and NPR, or most calculators will have NCR and NPR on them. Again, if your calculator doesn't, I'm not going to make you buy another calculator. Just get me to here. Get me to here. I would like to get this, but most of your points are in this section, not that section. Most of the partial credit, if you make a mistake somewhere, is here, not there. Okay, and that's it for chapter 2. I think we have a lot more time. 18 minutes, the things I can do in 18 minutes. Ready for chapter 3?
Let me. So listen.
Ooh, sa. anything up to now that raises a question? If not right now, I'm assuming I'm going to get an email, or on Wednesday I'm going to get a hand up, be like, hey, this thing. Can we do one more example of this thing? Because it's important that you get this, because although this is relatively simple in nature, it has long-reaching consequences to where we're going. Again, statistics is like a Jenga tower. It builds on top of each other. Okay. I'm enjoying the fact that I'm not talking for 30 seconds. So.
Do my homework. Are you gonna start chapter 3 or no?
Yeah, I'm going to start chopping. I'm just waiting for Sunny to finish copying. So. Good? Okay. The problem with whiteboards is that whiteboards, I write faster on a whiteboard than you can write in your notebook. Well, that's why I like chalkboards. On chalkboards, I have to put enough pressure on the chalk, which means I write slower, which means that you can keep up with me writing. All right. So yeah, there's trade-off. Plus, chalkboard unfortunately leaves marks on everything. Okay, discrete probability. Discrete probability. There's two. We can look at countable or finite. Now, there is also infinite, right, and continuous, but we're going to deal with that later. For now, we're just going to focus on countable and finite probability. And as with any other chapter, we're going to start with vocabulary. I've been told today that statistics seems more like an English class than math class. Unfortunately, I tend to agree. Okay, so vocabulary. Well, first one is the random variable. Random variable is a variable, let's call it x, that has a value for each outcome of a procedure that is determined by chance. So a random variable is a variable x that has a value for each outcome of a procedure that is determined by chance. Well, then we have probability distribution. Probability distribution, on the other hand, is a table. A table that gives the probability for each value of a So probability distribution is a table that gives the probability for each value of a random variable. Let's look at a very simple example. How about a 6-sided dice? If we have 6-sided dice, what are the outcomes? What are the values? Well, we have 1, 2, 3, 4, 5, and 6. What are the probabilities? What's the probability of getting a 1 on a 6-sided dice? 1 out of 6, 1 out of 6, 1 out of 6, 6, 1 out of 6, and 1 out of 6. And there is a probability distribution. Well, we are talking about a random variable, so let's talk about random variable. So there's discrete. There's a discrete random variable, which we are going to be dealing with in this chapter, which says a variable with a countable or finite number of values. If it's finite, it's countable. We can count things, even if it's a very big number, we can count it. If it's finite, we can count it. The one we're going to deal with later is continuous. Random variable. And that's a variable with infinite number So we have two random variables, is the discrete random variable and continuous random variable. Discrete random variables is countable and finite. There's the number of values is finite and countable, and then we have continuous random variable, which has an infinite number of possible values. Usually a measurement. We talked about it in chapter 1. Okay. I'm glad you agree. I'm going to shift this over because I'm not going to erase it because there's just a lot of text, and that will be. I want to keep on plowing. Again, those definitions are in the script I gave you, so I'm just going to assume that you have an access to those. All right, histograms. Because what statistics class will be. Don't smirk. Histograms are important. Histogram from a probability distribution. We have horizontal axis, and that's usually the values of random variable values, right? And then we have the vertical. And that's the probability. One example and we are done. Promise, because the rest of it I'm going to need more time to ramp up. So the example that I gave you on the die, the probability distribution of a die, that's boring. But we are a gambling bunch. So how about we roll my die? So So let's look at an example. Of Mr. N's die. Well, my die still has one. Actually, what? I'm just gonna put it over here. My die still has all the proper sides. Has 1, 2, 3, 4, 5, and 6. Otherwise, you know, why would we? I would get thrown out of Vegas. But my die rolls things differently. My die rolls things differently. I think we can gently assume that my die is weighted.
Some of the edges are shaped out.
I just put studs in my numbers. Just to be sure, I'm going to calculate the sum of all the probabilities. Because my way the die has 110% of rolling all the sides, there's probably something wrong with my calculations. All right. Well, and then I produce the histogram. 1, 2, 3, 4, 6. 0.05. We have 10. And behold the beautiful histogram for the probability distribution. Go ahead and take out this piece right here. And we're going to put a couple notes. Note number 1 is, if we are talking about probability distribution, we need to know if it's a valid probability distribution. And what does it mean, valid probability distribution? It means that somewhere between 0 and 1 is the probability. For every one of those, the probability cannot be bigger or smaller than 0 and 1. It has to be somewhere in between. So if you have a probability distribution and somewhere there's something lingering with a minus, that makes it invalid. You cannot deal with it. So that's first one. Second one, the sum of all the probabilities needs to be equal to 1. And so be careful, depending on when I write things, you can get a distribution probability doesn't either one of those two conditions aren't met. And that makes it invalid, which means that the question I ask, you can be like, hey, to the best of my ability, I'm going to try to answer, but the question is invalid. If you find a mistake like this on an exam, there's brownie points, lots of brownie points for pointing it out. Be like, hey, I cannot do it. This one, right now, looks great. But what happens if I was going to say, hey, that for the first one? Right? If my side 1 has 105% chance of happening, that's wrong. Same with this one. If I go minus 0.35, that also makes it invalid if I just put a minus somewhere. And the last one is the sum of all those probabilities. That number needs to be 1. Now again, since sometimes those probabilities are observed or rounded or calculated and rounded, that number not always comes out to be perfect 1.000. Sometimes it's 0.9997. That's fine. Or 1.001. So there's, if it's observed probabilities or calculated probabilities, depending on how you round, that number can be a little bit off. But if that number is 95%, you're screwed up. Right? So those are the two conditions for probability distributions. Each one of those needs to be between 0 and 1, and sum of all of those needs to be 1. And since most of you did at least one Sudoku in your life, I know you can add and make sure that things are correct.